Yeah, okay, so welcome back everyone to the so today is our pleasure to have Tizian Wenzel who will be talking about on the optimal shape parameter for kernel approximation. Yeah, thank you, Tizian.
Okay, thanks a lot for the great introduction. So I want to start with a brief motivation. And for this, we consider the following settings. So I'm now interested in interpolation of a function f, and the function f is assumed to be at least continuous, and we will have some more smoothness assumptions later on, for example, on a two-dimensional domain. And for this, we make use of kernel interpolation. And for kernel interpolation, we are now especially interested in radial basis functions. For example, you can think of the exponential kernel or the Laplace kernel. And these radial basis function kernels, they also have a shape parameter epsilon, which steers the width. And then, depending on the shape parameter, we see the plot on the right-hand side. So on the x-axis, you see the shape parameter, which I varied over some orders of magnitude. On the y-axis, we can see the error of interpolation. Here we measure the L2 error. And the red curve shows the interpolation error, depending on the shape parameter, if I do my interpolation based on 10 points. And now, we can ask ourselves, what is the best shape parameter here in this case? And maybe someone has a guess, or I can just tell you, I think it's pretty obvious. You should pick the shape parameter 1, because here for the shape parameter 1, we have the smallest error. And here in this talk, I would like to present some analysis why this is the best shape parameter, and the analysis will be based on sharp, direct, and inverse statements. And later on, we will also discuss how this setting applies to more machine learning style frameworks and so on. And now I would like to first start with an overview. So we will start with the motivation, which we saw already. Next, I will recall some background information on kernel, on reproducing kernel Hilbert spaces, and especially on power spaces, because they are the framework which we are working with. And then the first part will be on the sharp, direct, and inverse statements. So this is really the backbone of the theory. And then in the second part, we will come to the discussion of the optimal shape parameter, how this framework is applicable to this discussion. And then in the third part, we will see some applications and also some ongoing work. And we will conclude with a conclusion and some outlook. Okay, let's start with the background information on kernels. So as a kernel, you can think about, it's defined as a symmetric function from some domain omega times omega to the real values. And we will be interested in some Lipschitz domains. And two examples of such kernels are here the basic Mattern kernel, or also the linear Mattern kernel. And especially this basic Mattern kernel is also called the exponential kernel or the Laplace kernel, which is frequently used in machine learning. And these two examples of kernels are particular examples of radial basis function kernels, because they only depend on distance between data points and make use of this function phi. And now if we are talking about kernel interpolation, which is, I think, the most basic setting of kernel methods, then we consider a function, and I would like to have a continuous function at least on some Lipschitz domain, and we have some data points, which I also call centers. And then with help of these data points, we have some representer theorem, which tells us how our kernel interpolant looks like. And you can see this on the left-hand side here. So this is simply a sum of coefficients times these kernels. And here on the right-hand side, you can see the kernel interpolation conditions. So we would like to have our kernel interpolant in the data points equal to the function values, which we would like to approximate. And in the plot, in the bottom, you can see a visualization of such a radial kernel. And now if we have a couple of these kernels at different data points with different amplitude, it looks like this. Summing it up, we obtain such an approximation of a function. And then some more information on this kernel interpolation. How do we compute these coefficients? At least in theory, we can set up this linear equation system based on the interpolation conditions. This will yield this linear system here. And in particular, we see the kernel matrix here, which is hopefully familiar to most of you. And this kernel matrix will be positive definite because of our assumption on the kernel being strictly positive definite, and therefore this is always solvable. And now the analysis takes place in the reproducing kernel Hilbert space, which is just a Hilbert space of functions which is kind of native to the kernel. That's also the reason why it's sometimes called a native space. And in my analysis and in my talk, I want to focus on a particular class of kernels, namely so-called Sobolev kernels. And this simply means that the reproducing kernel Hilbert space is norm-equivalent to a Sobolev space. And this is the case for quite a lot of kernels, in particular for the Matern kernels, which we saw before, and also for other classes of kernels which are used in practice. And with this, we can have a look onto the shape parameter. Because for such radial basis function kernels, it's pretty easy to include as a shape parameter. This is a positive valued parameter, which we can simply put in front of our distance between the data points. And this simply scales the shape of the kernel, what we can see later on in the pictures below. And what is important for our theory is that the shape parameter steals the width of the kernel, but it does not change the reproducing kernel Hilbert space as a space of functions. And so, independent of the shape parameter, we still have the norm equivalence to our Sobolev kernel, to our Sobolev space. The only thing which changes are the constants which are involved in this norm equivalence. And here in this example, we see the linear Matern kernel with our shape parameter epsilon here. And here in the bottom two plots, we see on the left-hand side how our linear Matern kernel looks like for three different shape parameters. So you see the green one is more narrow, while the blue one is more flat. And on the right-hand side, you can see how this results in the interpolation of some black function. And you see with the green kernel, the shape parameter seems to be a little bit too peaky. Therefore, we have these kind of oscillations, while the orange or the blue one give a better approximation. And so this is really now the question, which of these shape parameters is the best one, which gives the best approximation. And with this, I would like to introduce some geometric quantities, which are helpful for the theory, and I will also comment on them briefly. So first of all, we will need the notion of a fill distance. This really measures how well my data points fill the domain. Then we also have the separation distance. This means how close the points are packed together, like the smallest distance between them. And then I also have this notion of quasi-uniformity, which is just the ratio of these two quantities, which means how well uniformly distributed my points are. And while I make use of these quantities for my analysis, they are not strictly required. So most of the theory can also be expanded beyond such quasi-uniformity settings. But for now, we will make use of these quantities and especially of the fill distance, which is a measure of how many points I have in my domain. Because the more points I have, the better my approximation will be. Okay, and with this, we can now have an overview of the kernel interpolation setting, which we discussed so far, and especially on the assumptions on which the theory will be built. So we will consider a compact Lipschitz region, and we consider a continuous kernel, which is norm equivalent to a Sobolev space. And for now, for the theory, I would like to consider quasi-uniform point sets. Okay, and with this, we can now have a look to the Mercer theorem and to power spaces. I think they might also be familiar to some of you because they provide a convenient framework for the approximation. So for sure, we need to have the kernel integral operator. The kernel integral operator is like this. We simply integrate a function from L2 against the kernel, which then gives another function. And this integral operator tk is a compact and self-adjoint operator because of their assumptions on our kernel, and therefore we obtain an orthonormal basis of normalized eigenfunctions. They will be called Bj, and also corresponding positive eigenvalues, lambda j. And with help of these eigenvalues and eigenfunctions, we can define power spaces. These power spaces will be quite important for our approximation later on for the analysis, and they are defined in the following way. So these power spaces, depending on a positive parameter bar theta, are subspaces of the space L2, and they are defined with help of such a weighted decay of those inner products here. And you can see for theta equal to 0, this will be the full space of L2, and the larger theta will be, the smaller the space will be, and therefore the smoother. And now we can see an overview of these spaces. And let me explain this figure here in detail. So we will start in the middle at the parameter theta equal to 1, because there we have our reproducing kernel Hilbert space, and below we have our Sobolev space. This is simply given because of our assumptions on the kernel. The kernel should be a Sobolev kernel. And now, if we go to the left-hand side, we see the space L2, and we have these two red arrows, which are either the space of, or the scale of power spaces, and on the bottom, the scale of Sobolev spaces. And we can see that, we simply have the power spaces here on the top, while we have the corresponding Sobolev spaces with reduced smoothness on the bottom. And by interpolation arguments, so we do here interpolation between spaces. If we interpolate this space with that space here, we end up with the power space in the middle. And the same can be done for the interpolation of the Sobolev space and the L2 space. And we obtain the space of reduced Sobolev smoothness. And with help of our interpolation theory, this norm equivalence from here carries over to the left-hand side here. And this regime here on the left-hand side is called the escaping regime, because we consider functions which are outside the reproducing kernel Hilbert space. So the theory kind of escapes the classical reproducing kernel Hilbert space theory. And then on the right-hand side, we have the superconvergence regime, because there we have increased smoothness compared to the reproducing kernel Hilbert space. And in particular, we see the Sobolev space of double smoothness with smoothness 2 tau, and we also see the image of the integral operator. So just the integral operator, which we discussed before. And the important thing here is now that this image of the integral operator is not equal to the full space h2 tau, but it's just a subspace, and in particular, usually a subspace given by some particular boundary conditions. And then also doing the interpolation in between 1 and 2, we also obtain the spaces, the power spaces in between, and the Sobolev spaces in between, and this subset relation simply carries over. Okay, this will be the framework we are dealing with, and we will see this later on again, this slide. Okay, and now I can briefly show you the backbone of the theory, the sharp, direct, and inverse statements. And for this, first I want to start with an overview. So here we just see the same figure again. So we have these two regimes, outside the RKHS and inside the RKHS. And then there are also two types of statements. We have direct statements and we have inverse statements. And so I would like to present this overview of the results here. So we see that in both the regimes, for both the direct statements and the inverse statements, there are a lot of results, and especially some results where I was able to contribute as well. And what we see here is that all these cases are covered. And now let's have a look into some details. So just to give an overview how these statements look like. The direct statements, they are always about smoothness gives you approximation rate. So we have some assumption on the smoothness of our target function, and with this we obtain some convergence rate. And Maybe you have seen such a standard error estimate for kernel interpolation. So here we really consider the difference between our target function of interest and our kernel interpolant measured in the L2 norm, and very classical estimates state that this error can be bounded by some constant times some worst case rate, which here depends on the fill distance, which means the number of points we have for our approximation. And here we have some LKHS residual. And then if we want to have a look into these two regimes, escaping and superconvergence, the statements look like this. And what we see in particular is that if our function is included in some power space with theta, then this really means that our approximation rate also scales like theta. And in particular, if our theta value is larger, that means in the superconvergence regime, we also have a larger rate of approximation. And yeah, so this is the statement of these direct statements. And I want to very quickly comment on the proof, just to give you some buzzwords, how this works. So this is just a statement. I would like to have a look into the proof. And the proof idea is to start with such a standard error estimate. And then we can squeeze out additional rates of convergence from this LKHS residual term here. And these additional convergence rates are based on the additional smoothness, then an application of the Hölder inequality with respect to these two spaces, and then finally some interpolation theoretical arguments. Okay, and that's it for the direct statements. And now I want to have a look into the inverse statements, and the inverse statements to really go the other way around. We start with some approximation rate and we can conclude the smoothness of the function. And here I also want to show the statements for both regimes. So we see in the regime where we are outside of the LKHS, we see usually some approximation rate. And then based on this approximation rate, we can really conclude that our function needs to have this kind of smoothness. And what is important, this parameter theta here is the same theta as here. And this minus just indicates that this statement holds for any theta dash, which is smaller than theta. And then in the superconvergence regime, we have the same kind of statement. So again, we see that we have some observed convergence rate. And with help of this convergence rate, we can conclude the smoothness of our function. And again, the statement is the same kind. We have the theta here and the same theta here. And then finally, we also observe some separation. So, and this saturation means in practice that we cannot approximate faster than 2 tau, because in case our approximation rate is larger than 2 tau, this needs to be the zero function. So there is no non-trivial function which we can approximate faster than 2 tau. And also here, I want to have a very quick look into the proof. The proof is based on the following. We consider such a nested sequence of points. So we build more and more accurate approximants. And then we consider this sequence of approximants. And essentially, we want to prove that this sequence of approximants is a Cauchy sequence. And in particular, a Cauchy sequence in this kind of space where we would like to have our function to live in. And how do we prove such a Cauchy sequence property? It's based on reproducing Kernel-Hilbert space properties. It's based on stability estimates, on error bounds, and on Bernstein inequalities. And then finally, having established such a Cauchy sequence property, we observe that this space is also a complete space. And then having a Cauchy sequence in a complete space gives us a unique limiting element F, which then coincides with F, and therefore we have established this statement. Okay, and now I want to have an overview of these direct and inverse statements, and the overview is presented here. Because we have a one-to-one correspondence. because we saw with help of our direct statements that if we have some smoothness of measured in terms of power spaces, then this means that we can approximate our function with a given rate. And now with help of the inverse statements, this also works the other way around. So if we can approximate a function with a given rate, we can also conclude that we have some power space smoothness here. And this is now really the important result here, that we have a one-to-one correspondence between this power space smoothness and the rate of approximation. And this will be now used in the following, because now we want to know how all of this connects to the shape parameter of the kernel. And this is exactly what we will now talk about. So this is this preprint here on the right-hand side. And let us delve into the details. So first of all, the precise assumptions which we are discussing. We saw before the case of a kernel with a shape parameter. So here you see the shape parameter epsilon and our radial basis function. And to have this analysis a little bit more general, we do not only focus on scalar value shape parameters, but we can really have a set of shape parameters, which could be a full matrix, which could be a kind of parametrized inner function, or a lot of this is possible. The only assumption which we really need in the end is that for any choice of parameter here, we end up with a Sobolev kernel. And therefore, this is called a parametrized Sobolev kernel, because in the end, we still want to have our kernel giving a reproducing kernel Hilbert space, which is norm equivalent to our Sobolev space. Okay, and with this kind of assumption, we can now start to work. And in particular, I want to revisit the theory again, the Mercer theorem, and especially the power spaces. And this is now kind of the same slide which we saw before. The only thing which I changed is that I included the shape parameter here. And so we see that we still have a kernel integral operator for any shape parameter epsilon. And this kernel integral operator looks exactly the same. And therefore, it's not too surprising that this integral operator is still compact and still self-adjoint. We still obtain an orthonormal basis and positive eigenvalues. But now these eigenfunctions and these eigenvalues, they also depend on the shape parameter epsilon. And therefore, also our definition of the power spaces will depend on the shape parameter. So we see that the shape parameter goes in here as well as here. And now, with help of this slight adjustment, we can have a look again into our figure on the overview of the spaces. So what we see here, we start again with our norm equivalence, which is simply our assumption on the parametrized Sobolev kernels. And then, with help of our interpolation arguments, the left-hand side of the figure, the escaping regime, stays exactly the same. Because if we interpolate between this space and that space, as well as this space and that space, the norm equivalence, which we have here in the middle, simply carries over to the left-hand side. So we have a norm equivalence here on the left-hand side, so not much changes here on the left-hand side. But what is changing is on the right-hand side. Because on the right-hand side here, we have this image of the integral operator. And what is important here is that our integral operator now depends on the shape parameter, and therefore this space here depends on the shape parameter. So we still have that our space is a subspace of the Sobolev space with smoothness 2 tau, but what is changing is what kind of subspace we have here. And in particular, since I mentioned before that this subspace usually is described in terms of some boundary conditions, it is these boundary conditions that change depending on epsilon. And then, with help of our interpolation theoretical arguments, also these subset relations carry over again. But let me stress this again, these spaces here are now different depending on the choice of shape parameter epsilon. Okay, and with this, we have still our same setting with the one-to-one correspondence, which we already saw before. So we have that a function f has some given power space smoothness, if and only if it can be approximated with some given rate. And now the important thing here is that these notions depend on our kernel and therefore on our shape parameter epsilon. And this means if I change the shape parameter of the kernel, this may change the power space smoothness of my function f. The Sobolev smoothness of the function f will stay the same, but the power space smoothness may change. And yeah, this is exactly what we see here on the right-hand side. And I will illustrate this with an example very soon. And this one-to-one correspondence now allows us to talk about an asymptotically optimal shape parameter. Because here we really see that the rate of approximation may depend on the shape parameter, and therefore the optimal shape parameter is for sure that shape parameter which gives the fastest rate of approximation. And we will also see this in a visualization soon. But first, I have a very easy example which shows how all of this works in practice. In order to be very simple, we consider a one-dimensional setup, so a domain which is given simply by the unit interval. We consider our exponential kernel here, and this exponential kernel for sure has some shape parameter epsilon. And what we know is that our reproducing kernel Hilbert space is still norm-equivalent to the Sobolev space H1 for any kind of shape parameter. And now I would like to approximate this following function. This is just a very simple polynomial, and this polynomial is for sure in the space H2. And now for purpose later on, let me calculate some boundary conditions of this function. And in particular, we see these two equations here that, yeah, these are the boundary conditions my function satisfies. And now on the other hand, I can also compute how my image of the integral operator looks like. And this is the calculation which is done here below. So the image of the integral operator of L2, depending on the shape parameter, is now given by all the functions of Sobolev smoothness 2, which satisfy the following boundary conditions. And here we can see that these boundary conditions look similar to the ones I calculated on purpose before. And we can see, yeah, and I also highlighted it in blue. And now we would like to have a fast rate of approximation. And in order to have a fast rate of approximation, we need that this function f is included in this kind of power space, in this image of the integral operator. And therefore, we need to choose the shape parameter of our kernel correctly, such that the function is included in our space. And we can see here that the choice of epsilon equal to 1 is the correct choice in this example, because this gives us, in the end, the correct inclusion into the power space, and therefore the best rate of approximation. So this was the example, and we can also see how this looks like in practice with our error plot. And for this, we take again a look at the plot which we already saw on the very first slide, where we considered the interpolation of our function with help of a shape parameter. And we saw that the shape parameter epsilon equal to 1 was very good. And we considered here only 10 data points for our interpolation or for our approximation. And how does this look like if we consider more than 10 points? And this is the updated figure, because here we can really see that having more points, like the yellow line, the green line, and the blue lines, we see that the smallest error is still obtained for the shape parameter epsilon equal to 1. And in particular, the dip gets deeper and deeper. And the reason for this is that for the shape parameter epsilon equal to 1, we have a larger rate of approximation, and therefore the error decreases there way quicker than for the other choices of shape parameter. And so we can really see that here in this example, the shape parameter epsilon equal to 1 is the optimal one, because for this choice of shape parameter, our target function of interest is obtained or is included in this superconvergence regime. Okay, and with this we can continue. And I would briefly highlight something, because the situation which we observe here on the left-hand side, which is just a plot from before, does not need to happen all the time. Because what can also happen, and which is way more frequent in practice, is the situation on the right-hand side. What is the difference between the plot on the left and the plot on the right? It's about the target function, which we try to approximate here. And what I was doing here for the target function on the right-hand side, I considered the same function f, but I added a small perturbation with a function g. And this function g was some function which is not included in this image of the integral operator. And then the situation looks really different, because we can see that for a small number of points, like the red line, the error curve looks pretty much the same. Because having only 10 points, the small perturbation does not have a large effect because it's small. But then having more points, for example, 600 points, the blue curve, our approximation error is in general way smaller, and therefore also this small contribution of the function g also has an effect. And this effect kind of destroys our optimal choice for our shape parameter here. And therefore we can see that there is really a difference between some asymptotic optimal shape parameter or some shape parameter which is only optimal in some pre-asymptotic way, which might not be the case in asymptotic considerations anymore. Okay, and then some more comments. What follows from the analysis is that in the left-hand side of our regime, there is no asymptotically optimal shape parameter. The reason for this is that independent of the choice of our shape parameter, we always have this norm equivalence. So the rate of convergence is simply determined by the Sobolev smoothness. And what more we have is that on the right-hand side, in the superconvergence regime, we can show that there always exists an optimal kernel. However, this optimal kernel does not need to be found with help of a single shape parameter. This is the statement here. So there might not be an optimal shape parameter, but it could also happen that there is a unique shape parameter, or we can also build examples where we even see multiple optimal shape parameters. And as we saw before, it's important to distinguish between some asymptotic regime and some pre-asymptotic regime. Okay, and with this, I can also comment on some ongoing work and some applications of this. And first of all, I want to consider some methods, or I want to comment on some methods which are used to optimize or to select a good parameter-dependent kernel. So usually your radial basis function kernel, for example, has the shape parameter, but you can also make use of more shape parameters like a full matrix, or you could also have some inner functions which you would like to optimize. And then there are different methods. For example, there is this leave one out cross-validation method, which was introduced by Ripper and analyzed and used later on as well. There are also strategies which work with effective condition number, or there's, for example, also some kernel flow optimization, which is also used by Boumediene. And the idea here is that the kernel is good if there is no significant loss in accuracy in the prediction error if the number of data points is halved. And most of these strategies, they work well in practice, but for some of them, it's not really well understood why they work and what's the theoretical reason for this. And the success of these methods, they can also be explained with help of this framework, with help of the theory, which I presented here. And this is, for example, ongoing work in progress. And one more interesting application of this work is also the use for neural networks. Because neural networks are nowadays used very much in practice, and we can carry over some of the results which I presented here also to the neural networks. For example, making use of the neural tangent kernel, because the neural tangent kernel is also a kernel, and therefore, yeah, this makes sense. And I will not delve into neural networks here or into the NTK regime now in detail, but I would just like to present a very brief overview of what is happening here. So neural networks have some activation functions, and in particular, we can consider the leaky ReLU as an activation function. And this activation function is given by the following formula here. And this alpha value is simply a scalar valued parameter, and this is exactly kind of a shape parameter. And this activation function parameter here then influences also the neural tangent kernel as a parameter. And here we can see exactly the same situation which we saw before. On x-axis now, I do not depict a shape parameter of the kernel, but I depict the parameter of the leaky ReLU function. So this is really a parameter of my neural network here. And on the y-axis, again, I have measured some L2 error approximation, and these error curves indicate the number of points which I use, and we can see that for sure, the more points I use, the smaller my error is, but also the choice of the correct leaky ReLU parameter alpha is also very important to obtain a small error of approximation. And especially we can see that a leaky ReLU parameter around 0.3 always gives the best results. And the reason for this is really that having a parametrized activation function means that I have a parametrized neural tangent kernel, and therefore this theory of the optimal parameter is applicable here as well. And with this, I come to the last slide of my presentation and the conclusion slide. So what we saw, first of all, was the theoretical backbone of the whole theory, the sharp, direct, and inverse statements, as well as the saturation. Then in the second part, we saw how all of this applies to a theory of asymptotically optimal shape parameters. And finally, we also saw some applications and some ongoing work. And with this, I would like to thank you all for your attendance, and I'm ready for some questions.
Yeah, thank you very much for the nice talk. Any questions or comments from the audience?